Hello, hello, hello. Can you hear me? Yes, you can. Great, cool. That check is so fun at the beginning. I'm never sure how this OBS thing works, so I can't bother to actually look at it properly. Hello again. Yay, I kept my promise. I'm actually on today. I didn't promise it, but yeah. Let's do Duolingo. Um, but I think I did this yesterday wrong. I should have said what I'm going to do first and then do Duolingo, right? Um, I'm just going to continue with the work I did last time, which was to just look more into the details of the Schrödinger equation. Schrödinger. Um, I think the main part was I want to know what kind of data goes in and what kind of data comes out of the quantized vector. Is that right? The quantum vector or whatever it's called, the bracket notation. So um, I'll double check that terminology. So that's what I'm going to do today, and this is all in mind of um, creating some kind of 3D visualization of interactions between electrons and atoms that they belong to. That's that out of the way. Another thing, I actually got a new. Oh, okay, we can load that up as well. I got a new lighting setup. Only one light, but I can change the light color, so it's pretty cool. Wait, let me try that. Because I got it in other rooms, but I wanted the office one, and they're kind of like they kind of cost too silly money, so I thought I'll wait on that one. But now I've finally got it, so yeah, we can. Oh yeah, check that out. Cool. So I'm on night mode at the moment because it's like late, but maybe I should be in a little bit of focus, so I'll get a little bit of blue back in, I reckon. So let's go for a nice purple, bit like that. Oh yeah, check that out. Okay, cool. Anyway, fun aside. Um, let's do this. So Duolingo first. Greek. We're on Greek. Oh God, yeah, we practiced those things. Interesting. We practiced those things yesterday. We didn't get any further. Um, so let's go
He.
further this time. He. So the X is a h.
He.
He. So it's probably that one. Ooh. Which one of these is the architect? O. R. He. Oh my God, not already. How can I yawn straight away when I open Duolingo? That is not a good sign. Um, O. Architectonas.
Ο αρχιτέκτονας.
O architectonas. Or, o architectonas.
Ο αρχιτέκτονας.
Architectonas. God. Cool though. It's good
He.
I can read it. He.
He. Όχι Μαρία.
Ochi Maria. I wonder what it means.
Όχι.
No, okay. Yes was nay. Nay and ochi. No, Maria. Match the pairs.
He.
He, ni. Oh, I know me. Let's do me. Me is,
Μη.
that's interesting. I didn't know that that was an I there, so, um, that's new to me. Ni,
Μη.
ni.
Ι.
E,
Γα.
ra. Ra. Oh yeah, we have learned these before. Damn it, I've just forgotten them. So this was me, I, and G, and here. Okay.
Όχι μαμά.
Ochi mama. No mum. Mum with an O. Didn't know that was a thing. Select the correct characters for chi. He is that
Χ.
one.
Ναι και όχι.
Ne, he,
Και.
ochi. So ne is yes, k is and then you've got the no. Ochi. Oh, it's got a little tick above it.
όχι,
Ochi. That is interesting. Is that shorter or longer?
ναι και όχι,
Ochi. Kind of
ναι,
feels longer, doesn't it?
χ,
He.
χ. Η Μαρία είναι αρχιτέκτονας.
He Maria in architectonas.
Η
He
Μαρία είναι
Maria
αρχιτέκτονας.
in architectonas. Oh my god.
Η Μαρία είναι αρχιτέκτονας.
He Maria in architectonas. Architectonas.
Η Μαρία είναι αρχιτέκτονας. Η Μαρία είναι αρχιτέκτονας.
Architectonas. Almost drops the R actually.
Η Μαρία είναι αρχιτέκτονας.
Architectonas. It's more like that without the A at all and the R. Interesting. I wonder what H
Τι.
is. Oh, okay. The feminine of. Okay. The Maria. Uh,
Είναι.
Ine is. Ine is. I guess it's just is.
Είναι.
Is, yeah. Is an architect.
Είναι.
Maria Ine architectonas.
Αρχιτέκτονας.
Okay. Oh. Oh, I see. Yeah, because it's not English. I see.
Η Άννα όχι η Μαρία. Η
Hiana.
Άννα. Η Άννα όχι η Μαρία.
Ochi Maria.
Μαρία.
Oh. Oh, okay.
Η Άννα όχι η Μαρία.
Ochi Maria. Oh my goodness, wow. Anna, not Maria. So is the H, let me just check this out. Let me just check this out. Ah, I do that every time. Every damn time. Whoops. Greek. H. Where are we looking at H? One, two, three, four, five, six. That is an H. And then what's it go? It goes capital. Okay, that's interesting. He. So that's why it sounds like an I. I see. I he. Okay. Let's go back to UK. Whoops. Cool.
Η Μαρία είναι αρχιτέκτονας.
Η Maria είναι architectonas. Maria is an architect.
Η Άννα όχι η Μαρία.
Η
Άννα.
Anna.
Όχι.
Όχι.
Τι.
Maria.
Μαρία.
He. Her. No, was it?
Η Άννα όχι η Μαρία.
It just kind of blends in. Hiana. Ochi Maria.
Η Άννα όχι η Μαρία.
Ochi Maria. It kind of drops on that one. Interesting. That was a good lesson. Oh yeah. Sure. I thought I already had them, but good. Oh yeah. Good stuff. Right, cool. That's that done. So, sip of a coffee and let's continue on. Decaf, of course, because it's way too late for real coffee. This is helpful again. Thank you. OneNote. I'd like to do a piece of software that actually works. That would be kind of nice. I don't know what that software would be though. There we go. Start to work now. Just gonna zoom out for a second. Just need to figure out where I was. Oh yeah, so we did this complex number thing. We kind of tried to visualize what the output of the bracket notation would be like if it were on a normal graph. Yeah, and then we were kind of labeling all the parts of these equations. I mean, let me go over. I won't look at what I've written. I'll try and guess or remember at least. So the I is the imaginary part that makes. I think it just makes everything imaginary because you're multiplying it by it. I don't know. This is the Planck constant. This is the amount of energy to emit an electron, I think. This is the partial differential because it's got the little curly d. This is the bracket vector, which is a vector in imaginary space, I think. I think it's like quantum notation or something. I can't remember what we saw it on the last video. I can't remember what it said there. And this is the waveform or the wave function. Um, and we found out this is psi, which is p in English for particle, and this is of time, is equal to the Hamiltonian. Hamiltonian was. Ay, ay, ay. Hamiltonian was. It wasn't space because I got that wrong. Hamiltonian is something about energy. It's a position. No. Yes. I remember it. The one example it said was in the case of gravity, the potential energy of an object uh, represents the notion of a Hamiltonian, which is that it's the energy without direction. So it's something that's not applied to, on a differential equation. I think that was it. And then we've got the same notation again for the bracket. So let's just double check. So Hamiltonian is an operator corresponding to total energy of that system. I think it was more in depth than that. I didn't write that down very well, did I? Let's just see if I can get that up. Oh, okay. Including both kinetic and potential energy. Its spectrum, the system's energy spectrum, or its set of energy eigenvalues, is the set of possible outcomes obtainable from a measurement of the system's total energy. Due to its close relation to the energy spectrum and time evolution of a system, it is of fundamental importance to most formulations of quantum theory. Um, where did we find that gravity thing then? I can't remember what that was about. Wasn't on here. Okay, maybe it was here. That's annoying. Gravity. No, okay. I don't know where. Oh, scalar potential. That's what it was. Infinite example is potential energy, so I need to make sure I don't get that wrong. So scalar potential, simply stated, describes a situation where the difference in the potential energies of an object in two different positions depends only on the positions, not upon the path taken by the object. And we found that this was intra. I think it was called intra. So you've got delta and del. Del is, oh, nabla, sorry. So what's intra? Intra, Greek. Symbol. I don't remember what I wrote about intra. Maybe it's nothing. Inside. Yeah, I don't know. Intra. Maybe I've got it written here somewhere. Oh, it's broken again. Come on. What keeps happening to that? Yeah, okay. It doesn't look like I wrote that down. Nabla and delta, fine. Um, and nabla was when you. Okay. Yes. So del is where you are finding the difference between vectors rather than finding the difference between two numbers, single numbers. think so. Uh, cool, let's go with that for now. So we go back up to the top here, if it lets me. Uh, yeah, so I think we want to start seeing maybe some variations of it, because I think we were looking at the, for non-relativistic, no, it was, I think this was related to relativity. A special case of the Schrödinger equation that admits a statement in those terms is the position space Schrödinger equation for a single non-relativistic particle in one dimension. So this is one variation or usage of it. And oh yeah, that's right. So we found out that this is when you add a position, or at least the function takes a position. Does it return out? I can't quite remember. How maths, right? So okay. So it says here the wave function, a function that assigns a complex number to each point x at each time t. It assigns a complex number to each point x each time t. So okay, so this is saying you pass in a t and out comes a complex number for x. So I'd like to know, okay, and so I guess it's showing you how that works maybe here. So you've got the plus bx. What is this actually saying? Can you even see this? You can perfectly, great. So it's saying the Schrödinger equation with this extra parameter of x, in which will be converted to imaginary, no, will be converted to a complex number, an imaginary number, right? That's the same, is it not? It's an element of a number system that contains the real numbers and a specific element denoted I, called the imaginary unit, and satisfying the equation I squared equals -1. Nuanced, okay. Moreover, every complex number can be expressed in the form a plus bi. Moreover, every complex number can be expressed in the form a plus something scaled with I, where a and b are real numbers. Because no real number satisfies the above equation, I was called an imaginary number by Descartes. For the complex number a plus bi, a is called the real part and b is called the imaginary part. Oh yeah, I've done practice on this actually. Yes, I remember this. Where did I start learning this? I was learning it from, I think, a YouTube video I watched. Might have to go to that again. That's very relevant here. Because there was some kind of rule set that you could apply to that term, that was then making things useful or creating useful things out of it. The set of complex numbers is denoted by either of the symbols complex or complex. Despite the historical nomenclature imaginary, complex numbers are regarded in the mathematical sciences as just as real as the real numbers and are fundamental in many aspects of the scientific description of the natural world. Okay. Complex numbers allow solutions to all polynomial equations, even those that have no solutions in real numbers. More precisely, so polynomial, poly means many, nomial probably means number, is it? Let's see. Etymology of polynomial. Many uh, oh, many names. Okay. So an algebraic equation or polynomial equation is an equation of the form p equals 0, where p is a polynomial with coefficients. A coefficient is a multiplicative factor in some term of a polynomial. Multiplicative, multiplication. A series or any expression. It is usually a number, but may be any expression. Okay. When the coefficients are variables, they are often called parameters. So where p is a polynomial with coefficients in some field, a set on which addition, subtraction, multiplication, and division are defined and behaved as the corresponding operators on rational and real numbers. A field is thus a fundamental algebraic structure which is widely used in algebra, number theory, and blah blah blah. On the other hand, a polynomial equation may involve several variables. In the case of several variables, the multivariate case, the term polynomial equation is usually referred to algebraic equation. Okay, so for example, sorry, x to the power of 5 minus 3x. This only this only has one term at the moment, plus 1 equals 0, is an algebraic equation with integer coefficients. Integer coefficients because because this scales to x, or is it that the x is scaling and because it comes out as 0, I guess. Okay, maybe. Yeah, is a multivariate polynomial equation over the rationals. So here's one variable so far, but then you've got then it becomes polynomial in this case. No, then it becomes algebraic because you have one variable still, but then it becomes polynomial because you've got your second variable. No, still not. It's this one here because that is when it becomes a multiplicative. Wherever it said that. Appears a polynomial with coefficients in some field, often the field. Wait, where did I just read that? Is it complex numbers that I? Where did I read multiplicative? Huh? Where's the? There is. Oh, that's weird. I have no idea where I just read multiplicative. Wasn't there, wasn't there. I know I read multivariate, but well, I am just confused. Fair enough. Oh, coefficient. That's where I read it. Okay. Let me just open my door, it's a bit hot in here. So, here's the thing. I don't know if I still understand this. I don't know if I understand this still. So, So this one's an algebraic equation with integer coefficients. That means, let's look at this again. It says a coefficient is a multiplicative factor in some term of a series or it is usually a number, but may be any expression. When the coefficients are variables, they are often called parameters. So in this case, you've got the coefficient of 3, but then the x is a parameter, so it's also a coefficient. Um, but I guess it just means a number. So I'm guessing then that's why it says with integer coefficients algebraic equation. And this one is multivariate polynomial equation over the rationals. What's a rational number again? Rational number is a number that can be expressed as the quotient or fraction of two integers, a numerator p and a non-zero denominator. So for example, negative 3 over 7 is a rational number, as is every integer. 5 equals 5 over 1. Oh, I see. The set of all rational numbers, also referred to as the rationals. The field of rationals, or the field of rational numbers, is usually denoted by a bold Q. Okay. And so it just means quotient. God damn it. Quantity produced by the division of two numbers. A quantity produced, so the quotient is the quantity of those two numbers. The rational number is the calculation. P over Q. Okay, so this is multivariate polynomial equation over the rationals. They're over them, so it's going to be the x and y is that polynomial part. Okay, that makes some sense. Some but not all polynomial equations with rational coefficients, so if that was like a 4, rational coefficients, have a solution that is an algebraic expression that can be found using a finite number of operations that involve only those same types of coefficients. That is, can be solved algebraically. This can be done for all such equations of degree 1, 2, 3, or 4, but for degree 5 or more, the degree of a polynomial is the highest of the degrees of the polynomials monomials single with non-zero coefficients. The highest of the degrees of the polynomials monomials with non-zero coefficients. The degree of a term is the sum of the exponents of the variables that appear in it. The sum of the exponents of the variables that appear in it. So this can be done for all such equations of degree 1, 2, 3, or 4. But degree is the degree of a term is the sum of the exponents of the variables that appear in it. So this can be done for all such equations of degree, but for degree 5 or more it can be only be done for some equations, not all. A large amount of research has been devoted to compute efficiently accurate approximations of the real or complex solutions of an univariate algebraic equation. See the root finding algorithm, and of the common solutions of several multivariate polynomial equations. See system of polynomial equations. Okay, that makes sense. The only thing is I'd like to understand what this one is then. So from what I'm reading, it means, because the degree says sum of, the degree of a term is the sum of the exponents of the variables that appear in it. So then the question is, what is the sum? What's the term? So I wonder if I click through to that, does it tell me what the term is? Degree of a term. Jeez. What a rabbit hole. Thanks, maths. You wanna rename everything to English, please? God. Um, I say that I actually quite like finding the etymology of stuff, but anyway. In mathematics, a monomial is, roughly speaking, a polynomial which has only one term. Two definitions of a monomial may be encountered. A monomial, also called power product, is a product of powers of variables with non-negative integers. Or in other words, a non-negative integer exponents. Or in other words, a product of variables, possibly repetitions. A monomial is called power product. Also called power product is a product of powers of variables with non-negative integer exponents. A product of powers of variables with non-negative integer exponents. That's interesting. It's not the product, it's the product of the powers of variables with non-negative integer exponents. So that, what is that one down from that? Oh, here we go. For example, x squared multiplied by y multiplied by z to the power of 3 cubed is a monomial. The constant 1 is a monomial, being equal to the empty product and to x0 for any variable x. Oh man, what does that even mean? Okay, let me try this again. In mathematics, a monomial is, how do you say this? How do you say? I'm so fed up of saying this to someone else and they're like, oh, that's not how you say it. It's like, oh, really? Does that really matter? God, apparently does.
Monomial.
Monomial. Okay, good. At least I'm not being an idiot like that. In mathematics, a monomial is, roughly speaking, a polynomial which has only one term. Two definitions of a monomial may be encountered. A monomial, also called power product, is a product of powers of variables with non-negative integer exponents, or, in other words, a product of variables, possibly with repetitions. I have to draw this. So let me jump to my episode 24 here. So it's saying, it is saying product of powers. So if you've got x to z and y to z, then it is the product of this and that. Right? That's what that means, right? Product of powers of variables. So these are the variables. Vars. These are the powers. Maybe that's not what powers means, actually. That could be why I'm getting confused. With non-negative integer exponents. Product of powers of variables with non-negative integer exponents. So does it mean that these powers are non-negative? Or does it mean that Product of powers of variables with non-negative exponents. Is a product of powers of variables with non-negative integer exponents. Or does it mean, so this is A, right, that, or does it mean B, which would be to the power of 3, to the power of 4, they're non-negative, and then they are powers of. So then it would be the sum of those powers, these would be the exponents that it's talking about that are non-negative. I think it's the first one. I just don't think it's written so well. My apologies, I don't know if it's written well because I don't understand it, but yeah. Then it says, for example, x2 and then yz3. So then we're kind of clarifying after that it's probably that these must be integers, they're non-negative integers, right? So I think that clarifies it. Um, the constant 1 is a monomial being equal to the empty product and to x0. The constant 1, okay, 1, here's my constant, is a monomial being equal to the empty product and to x0 for any variable x. So that maybe that's just an axiom. If only a single variable x is anyway, this is fine. So we get kind of a rough gist of this. So let's get the next one. And a monomial is a monomial in the first sense multiplied by a non-zero constant, called the coefficient of the monomial. So let's go back here. We don't need to go into that much detail for these things yet. Degree of a polynomial, great. Then we got the algebraic equations, good. So what's a polynomial? Is something with uh, the coefficient, or two coefficients, essentially. Multivariate polynomial equation over the rationals. And the rationals are this division thing. Okay, so polynomial, where did I see that? Here we go. Complex numbers allow solutions to all polynomial equations. I see, so if you can't come up with a real number or an algebraic equation that solves it, then you would then default to a complex number because that gives you a solution to that problem. Something like that. Even those that have no solutions in real numbers. There you go. More precisely, the fundamental theorem of algebra asserts that every polynomial equation with real or complex coefficients has a solution which is a complex number. So, more precisely, the fundamental theorem of algebra asserts that every polynomial equation with real or complex coefficients has a solution which is a complex number. Okay, for example, the equation x plus 1 squared equals -9 has no real solution. Oh, okay, I see. Yeah, since the square of a real number cannot be negative, but has the two non-real complex solutions, -1 plus 3i and -1 minus 3i. Okay, so I need to do a bit of research on that, but -1 plus 3i, that's 3 times 1 is 3x. So if I was to bring this down, it would be 3 times Oh, I'm not sure I understand how that works. Um, what's that powerful exponents? So that's plussing them. Um, oh, where's just a nice table? I think I've got a nice table somewhere here actually. Go to my notes. God, this could be risky. Um, yeah, that is risky. Let's not do that. Let's go back to that one. I do have notes of this. Damn it, let me go off the screen for a second. Ah, maths, here it is. Ah, yes, I've got it. I've got it. So yeah, sexy image. Cool. That sounds like me. Um, so this one is saying multiplied. This one, that one. Ah, here we go. So this is exponent inside. So I was just trying to think of um power of 0 equals 1, negative 1 over n times. So what, if I go back to this, um, x plus 1, so that's still not it. That's okay. So right, fine. That's great. I didn't realize so annoying that it's there. But anyway, it's kind of helpful in this project. Cool. Um, so what I'll do here is let's just try and figure this out. So it's saying x plus 1 squared is equal to negative 9 in a complex sense for minus 1 plus 3i, oops, or minus 1 minus 3i. So where does the 3 come from? Well, we have a squared, so um, if we pull that over there, I don't understand it. Gosh. If I were to pull that over there, it would be divided, right? So it's to the power. So what's the opposite of to the power of? That is log of. So it'd be log minus 9, right? What's that? Uh, oh, I can't do negatives. Oh, I see. Negative 9 log. Yeah, okay. That's gonna work. 3i. We have to figure this out because this is gonna be so serious, isn't it? X plus 1 equal to, oh, the power of 2 is equal to negative 9. Sorry for going silent for a second. So that's the complex solutions it's found there, and I wonder if it gives us a bit of information there. Um, this is beautiful. See Wolfram Alpha, dude. Good old Stephen Wolfram and his team. Um, that's plus 3i x. Where does that 3 come from then? Got to be something to do with the 9. So I mean, if you divide it by 9, is that it? Instead of log 9? Um, this is my maths flaws here, so I'm not very good at maths really. So how to solve how to bring exponent from one side of equation to other. I think it must be just the inverse of that. It must be division, which is not log. Let's imagine it's like that, right? So let's imagine it's going to be minus 9 divided by, yeah, so okay, so what's the log of 9 essentially? 9 log. It's not that. That is not right. Or is it the log of 9 log 2? No, 9 times, I can't remember how this works. Opposite of exponent. Given b to the power of e equals r, we have the nth root operation, b equals, oh, square root, of course. It turns out that this can actually be written as an exponent itself. Again, given b to the power of e equals r, we have e is equal to the log of b, r. Yeah, that's really sad that I forgot that. I completely forgot about square roots. Damn. Okay, so that's good. So that would be negative 9 square root 2, which is BE. Yeah, exactly. That carries there. That's good. So that will now be equals x plus 1. And then what we got now, so 2, no, uh, that, oh, is it negative 9? Then that? Invalid input, okay. So then we're going to minus 1, so x is equal to minus 1. No, it's going to be 2 negative 9 minus 1, which would be x is equal to, imaginary number because it's negative. So so hang on, this might be it then. So if you go 9, that is 3. So I think we've just found it, haven't we? Because it can't. So we put it to positive and then put imaginary number in. That's where that's come from, hasn't it? What is that? -1, -3i, or -1 plus 3i. Yeah, -3i makes more sense to me. But that's where it's come from. Okay, that's good. Okay, we get it. We understand that. We understand it. That's good. So, addition, subtraction, and multiplication of complex numbers can be naturally defined by using the rule I2 equals -1, combined with the associative, commutative, and distributive laws. Every non-zero complex number has a multiplicative inverse. Okay, this makes the complex numbers a field that has the real numbers as a subfield. So what is a field? A field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers do. A field is thus a fundamental algebraic structure which is widely used in algebra, num theory, etc. So I don't really understand that, but yeah, the best known fields are the field of rational numbers, the field of real numbers, and the field of complex numbers. Many other fields, such as fields of rational functions, algebraic function fields, algebraic number fields, and p-adic, p-adic fields, are commonly used and studied in mathematics, particularly in blah, blah, blah. The relation of two fields is expressed by the notion of a field extension, Galois theory, initiated by Évariste Galois in the 1830s, is devoted to understanding the symmetries of field extensions. Among other results, this theory shows that angle trisection and squaring the circle. Angle trisection. Cool, I like that. And squaring the circle can be done with a compass and straight edge. Moreover, it shows that quintic equations, phi is that, are in general algebraically unsolvable. So the regular heptagon cannot be constructed using only a straight edge and compass construction. This can be proven using the field of constructible numbers. I'm not sure that's very very well explained. Let's try this again. In mathematics, a field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers. So we've got a set. Let's just go. Can I just go down, please? Yeah. So we've got a set, and it says a field f is equal to a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers. So we've got a set of A, B, and C. This is F, so this is our field set. It's a set on which addition. So if I to do another one, A, B, C, we've got field 2. The addition of therefore the addition of F plus F2 are defined and behave as the corresponding operations on rational and real numbers. A field is thus a fundamental algebraic structure which is widely used in algebra and number theory. Is it saying that it's corresponding operations on rational and real numbers? It's just saying that the operation that it's basically that. It's saying that if you have f as a set of values, what do I do to add them together? Well, I do an operation defined by a field, and the field might be to iterate over each one and add it together. Or let's just get another let's get a second opinion in here. What is a mathematical field? A field is any set of elements that satisfies the field axioms for both addition and multiplication, and is commutative division algebra. An archaic name for a field is a rational domain. That's interesting. The French term for a field is Korb, and the German word is Körper, both meaning body. A field with a finite number of members is known as a finite field or Galois field. Just sit down again. Getting a lazy back here. Okay. So because the identity condition is generally required to be different for addition and multiplication, every field must have at least two elements. Examples include the complex numbers, rational numbers, real numbers, but not the integers, which form only a ring. It has been proven by Hilbert and Weierstrass that all generalizations of the field concept to triplets of elements are equivalent to the field of complex numbers. A ring in the mathematical sense is a set S together with two binary operators plus and multiplication, satisfying the following conditions. Additive associativity for all A, B, C as elements of S. A plus B plus C is therefore equal to A plus B plus C. Okay, fine. Need to revise that one, I think. Filled. So this was saying, let's try go back to where we were. This makes the complex numbers a field that has the real numbers as a subfield. The complex numbers form also a real vector space of dimension 2 with 1, I as a standard basis. Okay. 1 and the imaginary number is part of that set, or elements of that set. This standard basis makes that is compressed information. That is really compressed. Let's just highlight that because I think I need to understand that. I really need to understand that. let's call this, you can't see this, sorry, but notes. And I'll scroll down here. I'm just going to paste that. Oh, let me try that again. Put that there. Yeah. And I'm going to put need to revise this. Oh wow, that's small. Need to revise this. Okay. This standard basis makes the complex numbers a Cartesian plane, called the complex plane. This allows a geometric interpretation of the complex numbers and their operations, and conversely expressing in terms of complex numbers some geometric properties and constructions. For example, the real numbers form the real line, which is identified to the horizontal axis of the complex plane. Horizontal. Oh, that's interesting. I thought that that was the numbers, so I goes plus and minus. This is saying, for example, the real numbers form the real line, which is identified. Oh, yeah, that's right. Okay. The complex numbers of absolute value, one form the unit circle. Yes, okay. I see. The addition of a complex number is a translation in the complex plane, and the multiplication by a complex number is a similarity centered at the origin. Okay. The complex conjugation. Oh, conjugation. I can't remember what that is. Is the number with an equal real part and an imaginary part equal in magnitude but opposite in sign. So the conjugate of this. Oh, it's broken again. Maybe because I'm too far out. Maybe this is too big. Is that what's going wrong here? Maybe that's what that is. Let's go down. Make you smaller. Oh. What now? I can't resize this now. That's better. What? This is ridiculous. It just hasn't worked once today. Okay, so I'm paying for it as well. It's not like it's free. Okay, well, sorry. Yeah, shit happens with software, I guess. Um, it's just distracting me, that's all. What was I doing? I was I was going to say that yes, in this case, this would be the complex conjugate because we've gone from the where's my square root gone? We've gone from the -9 to a positive number here. I wonder if that's the complex conjugate there. It's the same magnitude but different sign. This seems fair. Why is that over there now? Ay ay ay. Let's just delete that. Let's move this up. Let's see if we can fix this problem. I think maybe I was a little bit too far out or something. It's too big for it. And now if I put that, need to revise this. Yeah, cool, okay. I think that's what that means. The complex conjugation is the reflection symmetry with respect to the real axis. The complex absolute value is a Euclidean norm. In summary, the complex numbers form a rich structure that is simultaneously an algebraically closed field, a commutative algebra over the reals, and a Euclidean vector space of dimension 2. So here's the question. If we're talking about that for the Schrödinger equation, which I'm going to copy out of here again, then what kind of numbers are we talking about, and what do they actually represent? So my understanding of this was governs the wave function of a quantum mechanical system. So let's say we're studying a particle, and we, as everyone knows, particles are now waves. So the particle is expressed as a wave using the Schrödinger equation. Cool. But the values of that wave are imaginary because you can't solve some of the polynomial equation without it. Something like that, I guess. Because if you look, I mean, look at this. This is just a geometric representation of the imaginary output of that equation. Complex plot of a wave function that satisfies the non-relativistic Schrödinger equation with v equals 0. In other words, this corresponds to a particle traveling freely through empty space. So cool. That representation, ah man, that representation, that's worrying. That is worrying. It's like, no, I know this has been confirmed experimentally, but it's it's so hard to detach from the kind of classical mechanisms of how we understand the world when we're not quantum physicists, right? Because what it means is in my work that I'm trying to do here, I will have a probabilistic area of movement for the electron, but to geometrically represent that with a 3D model and then use that to calculate forces from it seems really unpredictable, and this is where the problem must be, and this is why it's not being done. So, okay, how long have we been going for? An hour and 10 minutes. I think what I'm going to do here, you know what, I just really want to see some data though. I really want to see what kind of data goes in. I think it's so important here. So moving away from the equations, examples of usages of Schrödinger equation? What a wonderful question. This guy has no idea what he's talking about then. Oh, God. Um, like I feel like the questioner, the person asking the question is coming from my position there. Okay, fine. I think I'm asking the wrong question. Or so let's think about um electron position data for hydrogen. So let's read this then. Okay, so about electron position in ground state of hydrogen atom. Let's zoom into that. So it says, in this paper, according to Heraclitan dynamics, the the electron radial position in the ground state of hydrogen atom is introduced, i.e. R1 sub R sub 1 comma sub 2 is equal to R sub 4 plus or minus 1.2 multiplied by, is that lambda, subcompton of the electron. So we need to figure out what these are representing in physics. So Heraclitan dynamics and electron radial position in the ground state of hydrogen atom, pseudo Heraclitan dynamics on double surface and electron position radius. Okay, I don't understand that. The subject of interest of this paper is with the help of Heraclitan dynamics. How do you say this?
Heraclitean.
Heraclitean. Heraclitean. Heraclitean. Heraclitean. I think I got the wrong word there. Maybe they've got the wrong word. Fine. Where's that gone? Okay. To enlighten the electron position in the ground state of hydrogen atom. Sorry, it's kind of falling apart now, isn't it? Getting a bit tired, I guess. The ground circumstances. At Heraclitan dynamics, mass particles possess zero kinetic energy at the non-zero speed. It happens at the ground circumstances where mass, denoted m ground, and speed, denoted v ground, is related by the dynamic constant k as follows: m times x times v equals the square root of k. For the purpose of the present paper, it is convenient to express the speed in the units of official speed of light c as speed equals distance over time. God, let's just rework that one. Speed equals distance over time, and if they want to have c as a speed, If I want to get that down there, then it's going to be st, and that would be dt, so that's not what we're talking about here, no. Does kind of look familiar though. Hence, so why is that? So a ground, where mass denoted m ground, and speed denoted. Okay, so this is just a unit. Fine, okay. Hence 1, 2. M ground multiplied by a ground is equal to the square root of c of k over c. So let's just continue. I'm too tired for this now. The electron ground circumstances, taking into account k is equal to that, and c is equal to that. The electron with the ground mass is equal to that, has the next ground speed expressed in the units of official speed of light. The ground state of hydrogen atom. In the ground state of hydrogen atom, the electron possesses the non-zero kinetic energy, change in mass times speed of light squared, equals mc squared. This is the change in mc squared. And W stands for what? Okay. The concerned non-zero mass equivalent change in mass is related to the inverse fine structure constant. Applying 5 is evident that the electron non-ground mass is related to the inverse fine structure too. Okay. Um, two different speeds. A sub 1 is less than ground. A2 is belong to the non-ground mass m of the electron in the ground state of hydrogen atom. The above speeds are given solving the Panter-Rhe equation. For the theoretical inverse fine structure constant deduced from the double surface concept, for instance, the electron non-ground speeds A1 and A2 in the ground state of hydrogen atom are the next, and the average electron speed A in that state yields. Wait, what's numeric? I don't think it's what it means though. Complex number maybe. Okay. The electron path in the ground state of hydrogen atom. Ground state is an atom in which the total energy of the electrons cannot be lowered by transferring one or more electrons to different orbitals. That is, in a ground state, all electrons are in the lowest possible energies. I thought that was it. Okay. In the ground state of hydrogen atom, the electron circulates with the average speed on Bohr circumference of the length expressed in Compton wavelengths of the electron. With the lowest speed A1, the electron circulates below, and with the higher speed A2 above that average orbit. With the lower speed, the electron circulates below, and with the higher speed, above that average orbit. To pass the different circulation paths s in the same time t, the ratio of paths s should equal the ratio of speeds a. Hence, the same holds true for the corresponding circulation radii. Using the relations 13 and 14, the circulation circumferences and corresponding radii can be calculated. The mentioned data are collected in the table 1. Okay, here we go. The electron speeds, circumferences, and corresponding radii in the ground state of hydrogen atom. Higher position, circulation speed, circulation circumference. Let me just draw this, because I think this is quite relevant. So we've got nucleus. I think this is what this means. So the circulation speed, let's say this is a circle. So that is c is the speed from here to here, for example, is equal to 0.09. The circulation circumference is the length of this there's something very special about this, but I'm just trying to get an intuitive picture, and the circulation radius is this. Yeah. So this, okay, yeah, whatever that Compton thing is, but that's fine. That will be a circumference. So let's call this cm. So the higher position, average position, and that's it. Okay. It is evident from the table 1 that the proposed higher and lower electron position in the ground state of hydrogen atom is found at 1.2 wavelengths of the electron part from the Bohr radius, and the radial distance between both extreme electron positions change in r is the next. Following pseudo-Heraclitean dynamics on double surface, the electron should be found somewhere on its position radius. Expressed in Compton wavelengths of the electron, what is in accordance with the given result? The change in r is equal to that, which is less than. Okay. Conclusions. The proposed extreme radial distance between the electron positions in the ground state of hydrogen atom, change of r, is a consequence of Heraclitean dynamics. On the other hand, the electron position radius r is a consequence of pseudo-Heraclitean dynamics. The observed similarity of numbers shows the common essence of both aspects of the theory. Okay, let's take a look at electron position of hydrogen under an experiment. So let's do, yeah, here we go. This photograph shows the atom's electron orbital, the first time we have ever been able to observe the wave function of an atom. To capture this image, scientists used a quantum microscope, a device capable of seeing into the quantum realm. That's not helpful. Let's just have a look at this for a second. That's quite fantastic. When, when did this happen? 2013. Wow. Wow, isn't that something? That's what I need. That's what I need to simulate. Now, here's the thing, right? On the periodic table, let's go to the periodic table again. I can't quite remember, but I think it's just 1 on the atom the atomic number 1. Yeah. Let's go to that cool. This one. I really like this one. So it's got atomic number of 1, and the atomic number was what again? Number of number found in the nucleus. Number of protons found in the nucleus. Right, okay, so if we go back to that diagram, that picture, it shows the atom's electron orbital. So the problem here this is over a period of time. I wonder what a single snapshot looks like. Probability densities, yeah. Okay, okay, this is really good. This is really good. Okay. Oh, I've got a bit of reading to do, haven't I? Yeah. Okay. Look, as n, which is the, was it the oh gosh, I can't remember. What was the n? Let's have a look. No, I tell you what, I've got it in here. I have got it here. Everyone calm down. somewhere here at least. One of these. Here we go. So the principal quantum number cannot be zero. Um, that does not help. Here we go. Here it is. So the principal number n, as that increases, angular, no, the angular number increases. And so does the shape um, get altered. Okay. Oh shit, look at this. Lines are designated by H with a Greek subscript in order to decrease. Thus, the longest wavelength Balmer transition to say. So this, look at this image. Look at this image. You see these little dots? I don't know if you can see them on there. I bet this is. Oh my god, is that So I'm just wondering. I have no idea, but this is like the distance away from the center of the atom, is it? These transition frequencies correspond to spectral lines in the ultraviolet region of the electromagnetic spectrum. The lines for which n sub f equals 2 are called the Balmer series, and many of these spectral lines are visible. The spectrum of hydrogen is particularly important in astronomy because most of the universe is made of hydrogen. The Balmer series, which is the only hydrogen series with lines in the visible region of the electromagnetic spectrum, is shown in the right in more detail. N equals 1. No, I don't know if that is what I'm looking at. That would be exciting though, because basically I want to know like what the kind of data looks like that I'm going to be working with, and by just building up a little intuition, having a little look at some pictures, I think that will stir in me some thoughts about what the heck I'm getting into. Um, I think what I'm doing is right. It's going to take me a little while to get my head down into this and start to figure out what programs I need to make. Um, I also need to find a source for data. So I need to know everything that they know, those guys, um, and use that to my advantage. Now, I wonder if so, or I could backtrack from a protein and figure stuff out like that, which might be interesting as well. Um, Needless to say, it's a long journey, so I'm gonna call it a night here. Thanks for watching. If you did, don't think anyone did, although I don't really understand the numbers here. Um, as always, anyway. So keep learning, keep loving, and yeah. See you on the flip side. Ciao for now.